All right, now we're going to talk about events involving and. So we're going to look at the probabilities of two or more things happening in this section. In the past, we looked at just the probability of one thing happening. So when we do this, we have to ask ourselves if the second event depends on the occurrence of the first event. And we're going to look at both cases. So the first case is independent events. So two events are independent if the occurrence of either of them has no effect on the probability of the other. And so our formula for that is if you have two independent events, probability of A and B is the probability of A times the probability of B. So some examples of this are flipping two or more coins, or flipping one coin multiple times, spinning a spinner multiple times, drawing a card from a deck with replacement. That's going to be an important phrase. And then there's some hurricane and tornado questions we're going to look at. So our first example, you draw a card from a standard deck of 52, then the card is replaced. Okay, if it's replacement, that's independent. And then you shuffle it again. So the idea is we're going to draw a card. Okay, there's our card. 5. We're going to put it back in the deck. Shuffle it up. And then we're going to draw another card. Okay. So that's the idea. So find the probability of drawing a 2 the first time and a heart the second time. So it's not so much, we're not asking can these two events occur at the same time, because there are two events occurring. And so the probability of 2 the first, so I'll say first is 2 and second is a heart. Okay. Because we have without replacement, with replacement rather, with replacement, I'll just write that out. With replacement, that is independent. Okay. So basically, this is the easier case. We're going to multiply the probability that the first is a 2. We'll just come down here. Probability that the first draw is a 2 times the probability that the second draw is a heart. Okay, so the first one does not affect, the event of drawing a 2 and then shuffling the cards with that 2 back in there doesn't affect this second pull. So we should know that there's a total of 52 cards in a deck, so the number of things is 52, that's our denominator. How many 2s are there in a deck? We should be aware that there are 4, just in case we forgot that. I'm going to find all my 2s. Okay, so there's our 4 2s. So there are 4 2s in a deck. Now the question is, the second is a heart. So remember, we still have 52 cards in the deck because I pulled a card out, then I put it right back. We shuffled them up again. Oops. I'm going to have to reshuffle it. And so how many of those cards are a heart? Well, you should remember that there are 13 hearts in a deck. In fact, there's 13 of every suit. So what I would do I would try to type this into the calculator exactly like that. I'm going to make a real quick note. We replaced the first card drawn. So we have 52 still. I think it's good to write that down in case you get confused about this example versus the other. Like I said, let's try to do all of this at once. Parentheses, 4 over 52. Four divided by 52 times 13 divided by 52. You get this decimal, do second PRB, you get 1 over 52. So, that is our formula. So that is an example of an independent series of events. Let's look at an example of dependent. So let's go through that. So two events are dependent if the occurrence of one of them has an effect on the probability of the other. So a while ago we replaced the card, but if we had a similar example, we chose a card and then chose another card, well, we only have 51 left. So that changes things. So we'll talk about that difference. So the probability of A and B, if they're dependent, is probability of A times the probability of B given that A occurred. Some examples of that: drawing a card without replacement, and examples where food items are selected in succession and usually consumed. For instance, we have this donut question. We have a box of donuts. We got 2 dozen donuts in the box, all identical shape, size, shape, and color. 6 are jelly, 7 are lemon, 11 are custard. You randomly select a donut and you eat it, and then select another. So because you're eating a donut, that means you cannot replace it. So without replacement. Okay, if it's without replacement, it's dependent. So it's important to kind of dissect the question, figure out what you're looking for and what you're looking at, and then you can answer it. So we know it's dependent. Now, let's figure out what all we have. We have 2 dozen donuts. We should know that 2 dozen donuts is actually 24 total. Okay, 1 dozen donuts is 12, so 2 of those is 24. 6 are jelly filled, 7 are lemon filled, and 11 are custard filled. So we know that we have 24 total donuts. Let's write down all the donuts that we have. We have 6 jelly, 7 lemon, and 11 custard. Right? Go ahead and double check that 6 plus 7 plus 11 is, 6 plus 7 plus 11 is 24. Because in this question, 6 is written as a word, whereas 7 and 11 are written as numbers. So it's very common for students just to pick out the numbers and then ignore that. Okay. So the probability of selecting a lemon first, and custard second. So second is custard given first was lemon. Okay. So the probability that lemon is first times probability second is custard given first was lemon. So we have a total of 24 donuts. We have 7 lemon. That's the easy part. This is the hard part. How many donuts do we have left? We ate one of these lemons. We have 23 donuts left. Okay, so you might write that down just for your understanding. Now, the second one is going to be custard. How many custards do we have left? Well, we never ate a custard, but go ahead and write that down. This is how many custard we have left. And I say that because in the homework, if it was probability the first is a lemon and the second is lemon, well, we only had 7 to begin with. We ate 1, we would have 6. And they do that as well. So again, let's try to type this in the calculator all at once. 7 divided by 24 times 11 divided by 23. We get a decimal, second PRB. Ooh. Well, that's what's going to be happening. Turns out this one did not reduce any. So 77 over 552. That is a normal answer you're going to get, especially with the dependent examples. Okay. Sometimes the dependent examples do not reduce. If that happens, you'll have to reduce those by hand. But it's doable. All right. Then the last example I have is one I like to do in class or on videos because it's typically kind of tricky for some. Now I didn't include the entire question. Notice I just did B, C, D. That's because part A is basically the same as part B. So to save time on the video, I just cut out the first part. But if you understand this first part B, you'll understand part A. So here it is, tornado problems. This is actually going to be dependent. This is another example of dependent. I misspelled it. Dependent. Okay. So I'm already going to spoil that for you, but I'm telling you to make it a little easier. And the reason we know that is the probability a certain state will be hit by a major tornado is 1 over 17. So the probability of a tornado is 1 over 17. So what is the probability that a state will be hit by a major tornado 3 years in a row? So probability, I guess I can do first year tornado and second year tornado. You may not have to do, you probably don't have to show all of this work. This is really for your benefit of understanding why I'm working it like this. But eventually you'll get to where you know just what to type in. Okay. Because these are all Oops, I said dependent. Independent. Independent. Because the occurrence of this tornado happening doesn't depend on the previous year. So, sorry for that. And so, the probability of first year tornado, we'll start abbreviating so I don't run out of room. Second year tornado, and then third year tornado. Okay, I know it's getting messy. But each year, probability of a tornado is just 1 over 17. So what we're going to do is multiply 1 over 17 to itself 3 times. And notice that we're rounding 5 decimal places. So I don't have to worry about simplifying this one in the calculator. Okay? Now, I'll show you 2 things you can do. You can do 1 over 17 times 1 over 17 times 1 over 17. In fact, since I'm typing so many things, I'm going to do that calculation twice. 0.0002, 0, 5, 1, 2, 3, 4, 5. Okay, let's do it again. And some of you may be thinking there's an easier way to type this in, and you're actually right. I will do that, and I would prefer to do that. So, the easier way to type this in would be the following. 1 over 17 caret 3, because it's 3 years in a row. So rather than typing in 1 over 17 times itself however many times the question wants, you could do 1 over 17 caret 3, and then you get the number there. So this is probably easier if you understand that. But again, it's up to you. Both are correct. That's just the easier way to type it in. Now, this is the one that's going to give most of you trouble. So here we go. What is the probability the state will not be hit by a tornado in the next 10 years? Well, this is kind of a 2-part question. The first part, we have to figure out what is the probability a tornado will not hit in a single year. Okay, first, what is probability a tornado will not hit in a single year? All right, in order to do that, we have to remember that formula from a previous section, that the probability of E plus the probability of not E is equal to 1. Therefore, the probability of not E is 1 minus the probability of E. So, to figure out the probability of no tornado is 1 minus the probability of a tornado, which we did up there. So the probability of no tornado is 1 minus 1 over 17. Now, even though the final answer wants me to round 3 decimal places, I'm only on the first step to figure out the probability of no tornado. So I'm going to find the exact number using getting a fraction. So 1 minus 1 divided by 17, and then I'm going to convert that. Okay, so 16 over 17 Now, that's the first part completed. The second part says find the probability no tornado for 10 years. So probability of no tornado for 10 years is similar to what we did up here. It's going to be probability of no tornado, probability of no tornado, probability of no tornado. Written 10 times. I don't have the space to write it 10 times. But what I can do is no tornado, the probability of no tornado, and then raise that to the 10th. Okay. So we know the probability of no tornado is 16 over 17, and we're going to raise that number to the 10th. And I'm going to use the calculator here to do it, and I'm going to do it this way, 16 over 17. Because if I try to do 16 over 17 times itself 10 times, I will make a mistake. I do want a decimal, 3 decimal places, 0.545. See how it keeps going? It wants 545394323. We're going to go 3 decimal places. If that had been a 5, that 3, we would round up, but it's not. So that is my answer. That's the hardest one. That is the hardest one. Now, part D is no walk in the park, but it is a little easier if you understood that, or if you at least could get to that. Find the probability that a state will be hit at least once in the next year. This is the tricky thing you have to know. The probability at least once in 10 years is equal to 1 minus the probability of no tornado for 10 years. Okay, what's happening there? Well, the probability of at least one tornado, that means year 1 could have a tornado and none others, or year 2 has a tornado and none others, or year 3 has a tornado and none others, and so, or year 1 and 2 has a tornado and no others, etc. There's a lot of iterations that could occur. But at least one tornado in 10 years means that the complement, the opposite of at least one time, is none. So it'll be 1 minus that. Well, we've already done the work for that. Right there. And so we'll just type that in the calculator. Go ahead and clear the calculator and use just this one. 1 minus 0.545. 0.455. Because it wants you to round 3 decimal places, and we've already got this number here. They're basing this answer on what we got in that answer, or what the correct answer is on that answer. So just use that 3 decimal number.